Now we'll look at a couple of more interesting examples that show how useful reductions are for designing new algorithms. So again, that's the basic definition, and the implication of the definition is that in order to design an algorithm for a problem X, we can go ahead and use some existing algorithm for Y. And here's some of the many examples that we've already seen in this course. Finding the median and element distinctness I just talked about. The scheduling problem reduces to topological sort. We saw that in the shortest path lecture. Also the arbitrage problem of involves building a digraph for currency exchange. We reduce that to shortest paths. And there's several other examples. So it's an important and useful technique. So just the general mentality is, if I know how to solve Y and I have a new problem, can I use that to solve X? And every programmer does that, saying, well, I've got some code that solves Y, or I've got a library function that does Y. Can I use that to solve X? That's reduction. So our first example is the convex hull problem that we looked at briefly back in the sorting lecture. And that's where you're given endpoints in the plane, and what you want to do is identify the points on the periphery. That's called the extreme points of the convex hull. You can imagine a bunch of points on a big range, and a rancher wants to use the cheapest amount of fence to surround them all. So it's the minimum perimeter way to draw a line that surrounds all the points. That's the convex hull. And there's many other ways to define it. So that doesn't seem to be all that closely related to sorting, but it's actually true that convex hull reduces to sorting. That is, if you can sort, you can compute the convex hull, and that's an algorithm known as the Gram-Scan algorithm that we'll look at in the next slide. The cost of a convex hull is the cost of the sort, n log n, plus the cost of the reduction, and that Gram-Scan algorithm just uses linear time. So with sorting, we get an n log n algorithm for convex hull, which is a nice algorithm design technique. This is a diagram of that shows the Gram-Scan algorithm, which we won't go through in detail, but it's pretty intuitive. What we do is we pick a point, one over in the corner, maybe the smallest y-coordinate point, and then sort the points by polar angle swept out by that coordinate. So we think of a line sweeping through and just picking out the points by polar angle centered at that point. And we get the points in order along this polygon. And because we're doing it by polar angle, the lines don't intersect. It's a simple polygon, with no intersecting lines. And then the Gram-Scan algorithm is just to proceed along, over here, is to proceed along that polygon. But if you ever come to a point where you're going to make a right turn or a clockwise turn, you throw out the points that would have caused that. So in this case, this point would cause us to make a right turn, so we throw it out. And now our most recent points are these three. And again, that's a right point, so we throw that one out and puts us in this position here. And the idea is that any point that would cause a right-hand turn is not going to be on the convex hull. It's we kind of have a proof that the point's inside, just by dint of the fact that it would make us do a right turn. So we throw this one out, and that leaves that, and we go here, and that would be a right turn on our path. So throw that one out, and we're here, another one. And continuing in this way, when we finally get back to the beginning, we've computed the points on the convex hull. So the cost of the algorithm is the cost of the sort, which is n log n, but the cost of this scan is only linear. Every point only gets considered once. That's an excellent example of a reduction to get a new algorithm. If you didn't have the fast sort, this wouldn't be so effective. Here's another example of a reduction. We implemented and looked at shortest path for digraphs, What about shortest paths on undirected graphs? It still makes sense. So I have a weighted undirected graph with non-negative weights, and I want to find the shortest path from a given source vertex S to a given target vertex T, and that's just the lowest weight path from S to T. So how are we going to solve that one? We have shortest path that works for digraphs. Well, if we just replace each undirected edge by two directed edges, then the shortest path algorithm for digraphs works. In fact, with our graph representation, it's just running that algorithm because our undirected graphs are represented with edges going in both directions, so they're actually represented as digraphs. And again, what's the cost? The cost this time is the cost of pre-processing to just take the graph in its undirected form and convert it to directed form, and then the cost of shortest path in the digraph is E log V. So that gives us an algorithm for shortest paths in undirected graphs. Notice that it doesn't work if there's negative weights in the undirected graph, because the reduction creates a negative cycle. It is possible to find shortest paths in these graphs, but you need a much more sophisticated algorithm to do it. Just continuing in this way, we've considered quite a few problems that involve reductions. So I just talked about finding median and element distinctness and convex hull, reducing to sorting. And there were a bunch of other problems that we considered as exercises when we talked about applications to applications of sorting. So application of sorting really means problem reduces to sorting. So shortest processing time scheduling and lots of other problems that are reduced to sorting. And in the graph world, we looked at some pretty complicated problems, arbitrage. We looked at a parallel scheduling or CPM method, and I just talked about shortest paths and undirected graphs, and those all reduced to shortest paths and digraphs. We looked at problems that reduce to max flow. Bipartite matching reduces to max flow. And the linear programming problem that we'll talk about next time, actually both max flow and shortest paths and digraphs reduce to linear programming. So this is a pretty diverse set of problems that all through the set of reduction we found ways to solve them using some core kinds of problem-solving models. And so reduction is an extremely important algorithm design technique.